Okay, so we've got a bit of admin stuff to get through before the lecture. Firstly, the Math Olympiad. Okay, you know it from last year. 9 people have signed up, so there's 1 space left. Okay, so if you're still interested in doing the Math Olympiad, there's 1 space left if you want to apply. Okay, next, the assessments for this semester. So we've got class test 3 and class test 4. That will be counting 25% of the class mark. So it's a bit different to first semester. So first semester, we took best of the two. So if your class test 1 was better, I took that one. If your class test 2 was better, I took that one. For semester 2, we have to take the average. Okay, so both are counting this semester. Okay, and that will be 25%. Okay, and then with the exam, it's 50% of your class mark and 50% of the exam mark. And you'll need at least 40% class mark to write the exam. Okay, you know that from the 132. Okay, the scope for the 2 tests and the dates are as follows. So class test 3. It's pen. Okay, class test 3. This will be on the 16th of September. Okay, during the tutorial time, so 16th September, the scope will be on differential equations. Okay, so we'll be finishing that this week. Okay, so that's the first section. Then polar coordinates. Conic sections. Sequences. And series. Okay, so that will be class test 3. The marking will be the same as class test 1 and 2. Okay, so total marks are the same. Okay, class test 4. This will be on the 21st of October. So it will be a couple weeks before your final exam. Okay, so you've got class test 4. Then you'll get your final class mark. That will tell you if you're writing the exam or not. And then you've got 2-3 weeks and then the final exam. Okay, so from class test 4 to your final exam is really not much time. Okay, so please just keep that in mind because you're writing early November sometime. Okay, so class test 4, that will be on Taylor series, complex numbers, complex functions, and integration with complex functions. Okay, you can't hide from the integration. It's everywhere. Okay, so the last thing, integration with complex functions. Okay, and then once we're done with the integration of complex functions, that will be it for the year. Okay, so the scope for the final exam will be class test 1, class test 2. That will count 40% for your exam. So you just list out everything from class test 1 and 2. 40 marks from the exam will come from that. Then class test 3, class test 4, again, 60 marks will come from that. Okay, so that's the weighting for the final exam. And that is the same for the SUP exam. Okay, 40 marks from class test 1 and 2, 60 marks from class test 3 and 4. All right. Any questions on that? Okay. So then just the notes, I did mention this, but just to write it down, class test 3 and 4, that will count 25% of your class mark. Okay. And then I also mentioned this, but I'll write it down. you need at least 40% to write the exam. Okay. And the exam will be the usual 3 hours, either in the students' union or in the old mutual sports hall. Okay. Please check the timetable for that. Okay. So I don't know when it will be or which venue. You will need to find that out for yourself. Okay. Any questions? You're all good with that. Okay, so this week we're going to be going through differential equations. So I hope you remember some of the stuff from last year. So, what is a differential equation, where it's used, and so on. But this year we're going to be going through some different things. So the stuff we did last year is not a strict requirement for this year. However, it would be best if you know some of that stuff from last year. Okay, but that stuff from last year, that won't be tested. Right, so checking if it's linear or nonlinear, that won't be tested. The autonomous differential equations, that will not be tested. Okay, so differential equations. Okay, so firstly, an example of a differential equation, if you forgot from last year, is something like this. So we have some function a of x, let's say y double prime, plus some function b of x, y prime, plus c of x, y is equal to some f of x. Okay, so this is a second order differential equation, right? Because we got the y double prime, so it's second order. Okay, and we know that it is linear. So you can do the test for that. You can do that in your own time, but we know that this is also linear. So this is a second order linear differential equation. Yeah. So just to give you some recap on the terminology we use. So the order of the differential equation, that is the highest degree that appears. So here we've got y double prime, so that makes it second order. Okay, and you know what linear is. Okay, so last time, and by that I mean in the MATH160, okay, we were interested in types of differential equations. Right, so we saw differential equations from different areas. There was the one for electrical engineering. We saw some from chemistry, some from physics, and we saw those different types. Okay, we were also interested in the order of a differential equation. Right, we had some examples of first order, second order, third order, and so on. So we were interested in that. And we were also interested if the differential equation was linear or nonlinear. Right, and we had the test for that. So that was last year. So this year we're going to look at something different. Okay, so we are now interested in. Okay, and there will be 3 sub-chapters that we'll go through this week. So this double and the single, that will be one of the chapters. And then the next double that we have on Thursday, we'll go through the last one. Okay, so number 1, existence and uniqueness of solutions. Okay, so what we mean by that is given a differential equation, firstly, existence, are there solutions to the differential equation? Some differential equations might not have a solution. Okay, so we're interested in existence and uniqueness. If the differential equation has a solution, is there only one of them? So does that make it a unique solution? Or are there like 3 of them or infinitely many? Okay, so that is under uniqueness. Number 2, initial conditions and boundary values. Okay, this will become very important for the mechanical engineers later on. Okay, so initial conditions, you know that from physics, right? You throw a ball up, there's some initial position, there's some initial velocity, and it makes that parabola, right? So whatever you start the experiment with, that is your initial condition. So initial position, initial velocity, whatever that might be. Boundary values, we'll get into that a bit later on, but that you'll see quite a lot later on for the mechanical engineers. Okay, and number 3, solution methods. Okay, so this last chapter will be the largest chapter and will be on actually solving these differential equations. So depending on the differential equation given to you, there's a number of methods you can use to solve it. Now, as soon as I say a number of methods to solve it, right, you must think about your bonus marks. If you solve the differential equation 2 different ways, you get the marks for both, right? Same as we had before. Okay, so I'll put a little star here. Remember, multiple ways, you get your multiple marks. Okay, so just keep that in mind if you want your bonus marks. Okay, so let's start on the first chapter, existence and uniqueness of solutions. Okay, so we're going to start off with a very simple differential equation, just to get the idea across, but this method applies for anything that's given. Okay, but we'll start off simple. Okay, so consider the differential equation. Okay, y double prime plus y is equal to 0. Okay, so immediately think to yourself, it's second order because of the y double prime, and it is also linear. Right, you know the method from last year. We won't go through that again, but you can check that. So this is second order, and it is linear. And we can try guess some solutions to this, but I'll put them down for you. So y of x is equal to a cos x. That's a solution. So let's check that. If we take the first derivative, what do we end up with? What do we get? First derivative. Negative sign. Yeah. So y prime, that will be minus a sine x. If we do the derivative again, negative cos, yeah. Okay, so what happens if I take y and I add it to y double prime? They cancel, yeah, and we get 0. So this is in fact a solution. So y of x equals a cos x, that's a solution. But also, y of x equals b sine x, this is also a solution. It's a different solution. So the first one, y of x equals a cos x, that's one solution. We check that it works. y of x equals b sine x. It's different, but it also works. So let's check that. So y prime, that will be a cos x, and y double prime, that will be minus a sine x. And again, if we take y double prime plus y, it cancels and we get 0. Right, left-hand side equals right-hand side. So both of these are solutions. So a cos x is a solution. And b sine x is also a solution. Okay. So we have two different solutions for this differential equation. Now, what's interesting is since this is a linear differential equation, if we have two solutions, the sum of them is also a solution. So if I take a cos x plus b sine x, and I'll take the combination of them, this is also a solution. So a cos x, that's a solution. B sine x, that's also a solution. We check that. A cos x plus b sine x, that is also a solution. Okay, so we call this a general solution. Right, so we got a cos x and b sine x. Those were two solutions that we found. Adding them together gives us what is called the general solution. So for homework, please check that that is in fact a solution. Okay, so a general solution includes both. Okay, and this might be a new word to you. I don't know if you covered this in Math 132. Includes both linearly independent solutions. Did you cover that in Math 132? Okay, good. So you would have done that with vectors. We're going to do a similar thing with functions, but the idea is the same. Okay, so whatever you learned in your 132, that applies to this. But instead of linearly independent vectors, we now look at linearly independent functions. The idea is exactly the same. So both linearly independent solutions. Okay, and again, those are a cos x and b sine x. Okay, and then just a little fact for you to remember. In general, an nth order differential equation has n linearly independent solutions. Okay, so if I give you a second order differential equations, you should expect two linearly independent solutions, like we had with the sine and the cos. Then your general solution will be the sum of the two. If I give you a third order differential equation, then you will have, in general, three linearly independent solutions, and then your general solution will be the sum of the three. Yeah. Okay. And again, this is in general, not always. Okay, sometimes you won't have that, but you should expect, if it's second order, two linearly independent solutions. Okay, definition. So I'm going to rewrite the definition for linearly independent vectors like you saw before, but this time it will be in terms of the solutions. Okay, again, the idea is exactly the same from what you covered before, but just replace vectors with solutions. Okay, that's the same thing. Okay, a set of solutions. Okay, again, before you would have said a set of vectors. So a set of solutions is called linearly independent. If each solution, again, each vector, same idea. If each solution can't be written as a linear combination or sum, same thing. Sum of the other solutions. Right, just replace solutions with vectors, and you've seen that last semester. Okay, so let's have a look at some examples. So the one we just saw, sine x and cos x. Okay, these are independent. Okay, so you can take sine x and cos x. You can multiply cos x by whatever you want. It will never become sine x. If you have sine x, you can multiply it by whatever you want. It will never become cos x. They are independent of each other. Okay, another example, 3x and x squared. These are also independent. Okay, so you take x, you multiply it by any number you like, it will never become x squared. You take x squared, you can multiply it by whatever number you like, it will never become 3. Those are independent. And the last example, we have 3x and 6 minus 2x. This is dependent. Why? Well, because 6 minus 2x, we can write it as 2 times the first thing minus 2 times the second thing. That is a linear combination of what's in the set, and so it cannot be independent. So here 6 minus 2x, that is 2 times the first thing minus 2 times the second thing. So clearly it is not independent, right? It depends on the first two. So here, the third element, six minus 2x, depends on the first two, and so can't be independent. Right? Because if it depends on the first two, it can't be independent. Okay, and you'd have seen more of these examples with vectors. Okay, any questions so far? All good. Okay, so we've done these 3 examples here just by inspection, right? So we looked at the elements and we checked if they are independent or not. However, there is a better method to check. So we can check for linear independence. Okay. On an interval AB. Okay, so I didn't specify this for the previous examples, but when you're checking linear independence of functions, you need to specify some interval. So if the interval is not given, we just assume the interval is the whole real line. Okay, otherwise there will be some interval that's provided. Okay, so otherwise AB is just the real number line. Okay, so if the interval is not given, you can just take it that the function is over all of the real numbers. Okay, using the Wronskian W. I don't think you covered that in 132. Okay, so what is this Wronskian? So it is a function, wx, and is equal to the determinant, so you know what that is, of f1 up to fn, where those are the functions that we're checking. So here, back to these examples, f1 will be sine x, f2 will be cos x, okay, for that one. In the second case, f1 will be 3, f2 will be x, f3 will be x squared. Okay, it's whatever is in the set we're checking. Okay, so we take that, and then we take the derivatives on each row. So row 1, that's the functions that are given. Row 2, that's the functions with the first derivative. Okay, so we take the first derivative for that row. Then the third row, we take the second derivative, and so on, down to the last row, where we take the n-1 derivative. Okay. So going across, we're going to have n columns. Okay, one column for each function. And going down, we have n rows, one for each derivative. So the 0th derivative, which is just the function, down to n-1 derivative. So in total, n. So we have n columns and we have n rows. Okay, once we have the square matrix with n columns, n rows, we then take the determinant. Okay, and that will give us our function w. Okay, now once we have our w function, we can then use that to check if the f1 to fn are independent or not. Okay, so number 1. So there's 2 cases we need to look at. So this is case 1. So if the Wronskian w of x is non-zero for at least one value of x, okay, so we've got w on some interval ab if it is non-zero for at least one value of x. So if you substitute one value of x and you get some number different from 0, then we're looking at case 1. Okay, so at least one value of x in the interval ab. Okay, then the set of functions is linearly independent. Yeah, again, so for case 1, we find our w function. If the function is non-zero, so different from 0, positive or negative, but not 0, for at least one value of x. So if you find just one value of x where it's non-zero, then the set is linearly independent. Okay, and then obviously for case 2, that's the opposite. If the Wronskian w of x is 0, right, it's the opposite of 1, so for all values of x, for all x on the interval, okay, then the set of functions is linearly dependent, right? It's the opposite of case 1. Okay, there's a little star to this, so it's a very small condition, but we can actually ignore it. Okay, so the little star. The functions must be smooth functions. Okay, but it's a very small condition. We're going to be ignoring it because we will always work with smooth functions. Okay, so very small condition, but since we're only going to be working with smooth functions, you can actually ignore that. Okay, but it is important to know, if it comes up in a true or false question in next week's quiz, something to know. All right, any questions about this so far? You're all good. Okay, so it's either case 1, where it's linearly independent if it's non-zero. Otherwise, case 2, it's the opposite. If it is 0 for all x, then it's dependent. Okay, let's have a look at some examples of this. Okay, so let's go through that list that we had earlier. So we did these 3 by inspection. So we got independent, independent, dependent. Let's check now using the Wronskian to see if we were correct. Okay, so number 1, we had the sets sin x and cos x. Now here the interval is not given, so we take it as the whole real number line. Okay, so we need to calculate this w, so that's equal to the determinant. Now, there's different ways of writing the determinant. We could write it like this. So the determinant of sin x cos x, and then we need to take the derivative. So the derivative of sin, that's going to be cos, and the derivative of cos, that's going to be minus sin. Okay, so you can write it like that. There's another way you probably would have seen with that vertical line. So sin x cos x minus sin x. Okay, it's just notation. Use whatever you like. I don't care. Okay, so we want the determinant. So this is going to be sin x times minus sin x, so minus sin squared. Okay, and then minus cos squared. Okay, but minus sin squared minus cos squared, that's minus 1. And minus 1 is definitely non-zero. If it's non-zero, that's case 1, so it's linearly independent. Okay. Any questions for this first example? Okay, pretty straightforward. The next one, so this was 1. Number 2, we had the set of 3x and x squared. Okay, and we want to check. So we set up the determinant. So w of x is equal to the determinant. But now it's going to be a 3 by 3 because there's 3 functions there. So this will be 3x and x squared. Okay. And you should know from your determinants that the order does not matter. Everyone know that? Okay. So the order that we put those in, that does not affect the determinant. Okay, next row, we need to take the derivative. So that will be 0, 1, and 2x. And then the next row, we do the derivative again. So that will be 0, 0, and 2. Okay, so here we have a 3 by 3 determinant. So you know how to do that. You will not be tested on 4 by 4. Okay, that's just too much work. It's a waste of time. If you can do 3 by 3, that's good enough. Okay, maybe the homework problem will be 4 by 4, but actually in a test, you will not get that. Okay, so this is going to be 3 for the first element there. Then we're going to have 2 minus 0 minus x. And then you can just check that. We got the zeros there, so there'll be 0 plus x squared. And again, we got the zeros there. Okay, so 3 times 2, that will be 6. That is definitely not 0. So we go to case 1. So it's linearly independent. All right. Any questions for the 3 by 3? Yes.
Is it possible if you just take the diagonal side?
Oh, because it's upper triangular. Yes, you can do that. Yeah. Yeah. So whatever tricks you know for the determinants or product of the diagonals, you can do that. That's perfectly fine. If you did not know that, then you can always do it the long way. Okay. But yeah, that's fine. You can do it like this. So this will be 3 times 1 times 2. That will be 6. Perfectly fine. Just a note for tests, the amount of time you are given is assumed you do it the long way. Okay. So you'll be given time to do it the long way. If you do it the short way, you save yourself the time. Okay. But that's entirely up to you, however you want to do it. All right. Any other questions? Okay. Then the last one. Okay, so here we had the set 3x and 6 minus 2x. Okay, again, it will be a 3 by 3 because we've got 3 functions there. So let's set it up and check. So we've got 3x and 6 minus 2x. Okay, next row, we take the derivative. So that will be 0, 1 minus 2. Next row, we do the derivative again. So that will be 0, 0, 0. Now here you can use your determinant tricks. We have a row of just zeros. So the determinant is 0. So we actually don't need to do anything further. We can just say straight it's 0. But if you want to do it the long way, that's fine as well. Okay, but we end up with 0. Now, remember what the case, if we go back up here to the cases, case 2, if it's 0 for all values of x, then it's linearly dependent. Okay, well, this is 0 for all values of x, so it's linearly dependent. So yes, this does match up with our inspection method that we did earlier. All right. Any questions on the Wronskian? All good. Okay. So nothing, we can move on. You're all good. Okay, so let's go back to our example from earlier. Okay, so this was the y double prime plus y is equal to 0. Okay, so back to the easy example we had at the beginning. So now we know that cos x and sin x are linearly independent. They are both solutions. So the general solution is y of x is going to be a cos x plus b sin x. Okay, so this is where we left off before we did the whole Wronskian stuff. Okay, so we have 2 linearly independent solutions. Okay, and then just a side note, which we proved using W. Okay, so we proved that they were linearly independent. But this A and B, those were just some constants. We actually don't know what they are. But A and B are still unknown constants. Okay, and if they are unknown constants, they can be anything. So A and B are just some, real numbers. So A can be 2, B can be 3. We have a solution. A can be 1, B can be 1. That's also a solution. So for any possibilities of A and B, we get ourselves another solution. So we have infinitely many possibilities for A and B. Right? So we can have A is 0, B is 1, both of them being 1, A is 1, B is 2. Right? You can pick whatever you like. We end up with infinitely many possibilities. So if we have infinitely many possibilities for A and B, we have infinitely many possibilities for this y of x. Okay, for the general solution y of x. Okay, now at this point, I must warn you not to confuse the general solution with the linearly independent solutions. So this equation has two and only two linearly independent solutions. That was the sine and the cos. However, there are still infinitely many general solutions. Okay, please do not mix that up. Okay, again, two linearly independent solutions, infinitely many general solutions. Okay, we can get this down to a single solution. A single unique solution. Okay, using an initial condition. Yep, that's number one. Or some boundary values. Yeah. So before we use initial conditions or boundary values, there are infinitely many possibilities, right? A and B, we don't know what those are. If I then provide you with some initial condition or some boundary value, then the number of solutions go down to 1. And that solution will become unique. Okay, so let's have a look at these two in some detail. So number one, initial conditions. Okay, and again, to think about what these are, think of your physics problem. So if you throw a ball up, there needs to be some initial height, some initial velocity. Okay, that's what starts the process. Then the ball does its thing, comes back down, but it's those initial conditions that set it up. So you're standing here, you throw a ball up, there is some initial height, let's call that y0, and some initial velocity. You need both. You can't just have an initial height, you need both an initial height and an initial velocity. These two combined are the initial conditions. And we'll see in a bit why we need two of them. Okay, so you always need the initial position, initial velocity. That's two pieces of data. So why do we need two? Well, because it's a second order differential equation, right? You know your Newton's law, F equals ma. That is the second derivative of position. So it's a second order differential equation. So we need two initial conditions. Okay, that's where it comes from. So we require two initial conditions to solve for A and B. since there are two unknowns. Okay, so two initial conditions for two unknowns. How did we get the two unknowns? There were two linearly independent solutions. How did we get two of those? It's second order. So all of those numbers give us the same thing. So two unknowns, that comes from the two linearly independent solutions. Okay, how did we get two linearly independent solutions? Well, because it was second order. Okay, so if it was a third order differential equation, we would have three linearly independent solutions. We would have three unknowns, and therefore we would need three initial conditions. Okay, let's have a look at an example. Okay, so let's say we have our solution. So we found the solution for A and B, and we want to determine what those values are. So we'll go back to what we started with. So that was A cos X and B sin X. Okay, and again, we need two initial conditions. So whatever the solution looks like, let's say it looks something like this. We need an initial value. So when X is 0, Y is something, we need to know what that is. So that is our first initial condition. And secondly, like before when we had the position and velocity, we need the gradient at that point as well. Okay, so at X equals 0, we need to be provided with the value of Y and Y prime. Those are the two initial conditions. Okay, so let's say those are given as Y of 0 is 1, and Y prime of 0 is minus 2. Okay, so initial position, initial velocity. Okay, so let's see what we do. Well, two equations, two unknowns, right? We solve it simultaneously. So first equation, y of 0 is 1. So we're going to have A cos 0 plus B sin 0 is 1. We call that equation 1. And y prime of 0 is minus 2. So we need to take the derivative. So we're going to have minus A sin 0, and then the derivative of sin, that will be cos, plus B cos 0 is minus 2. Equation 2. Two equations, two unknowns, we can solve simultaneously. Okay, you can do that for yourself, quite easy, because sin of 0 is 0, so that goes away. Cos of 0 is 1. Okay, so it becomes very easy to solve. You can check, we end up with A equals 1. Right, because the B goes away, so A is 1, and B is minus 2. Okay, very easy to check. Okay, so now we have the values of A and B. We can then write the final solution, which is unique. There's only one of them, because now we know A and B. So we can write y of x is A, which is 1, so it's going to be cos x minus 2 sin x, and that's it. No more unknowns. This is fully determined now. Okay, we call this the particular solution. Okay, so we've got the general solution, that's with the unknowns, and then the particular solution, that's with the unknowns filled in. Again, general solution, that was just that linear combination of linearly independent solutions. Okay, once you provide your initial conditions, we get this final solution here with no more unknowns. Any questions on this? You're all good. Okay, so that is initial conditions. Next, we have boundary conditions. So very similar idea to initial conditions. We need to be provided with some pieces of data, so 2 of them for second order, and that will allow us to solve for A and B. So number 2, boundary values, or you might see this as boundary conditions. Okay, right, it's just wording, but boundary values, boundary conditions, you might see it like that. Okay, so we require 2 boundary conditions. Okay, to solve for the 2 unknowns A and B. Okay. Again, the number 2, because it's second order, so we need some boundary condition number 1 to solve for A, and boundary condition number 2, and then we can solve for B. Okay, let's have a look at an example. So we're going to have our solution like we had before. A cos x plus b sine x. Okay. And then we need values at the boundaries of our solution. So we're going to have something like this. So our solution might be something like that. We're going to have a starting point, and we're going to have an ending point. Okay, those are the boundaries to the problem. So whatever the solution is, we're going to say it only starts at that first point and it ends at the second point. So let's say it's from 0 to pi over 2. So we're only interested in the solution from 0 up to pi over 2. So we can provide our boundary conditions as y at 0, let's say is 0, and y at pi over 2, let's say that's 1. So at the starting point, we provide the value of y. At the ending point, we provide another value of y. Okay, so starting point, ending point, you can also call those the boundaries, something like that. Okay, so these are the boundary conditions. Okay. And again, we've got 2 of them. We've got 2 unknowns. So we set up a system of equations and we solve simultaneously. So for the first one, y of 0 is 0. So we're going to have a cos 0 plus b sine 0. This must be 0. Okay, that takes care of equation 1. So we can call this equation 1. And secondly, y at pi over 2 is 1. So we're going to have a cos pi over 2. B sine pi over 2 is 1. Now there's no derivatives, okay, because these are boundary values. It's values for y. So equation 1 and equation 2 is just the y equation. No derivatives mentioned at all. Okay, this is very easy to solve, right? Sine of 0 is 0. Cos of pi over 2, that's also 0. So those go away. So A must be 0. And B must be 1. So we get our solution. Just subbing that in. Y of x will be sine x. Okay, and that's it for our particular solution. All right. Any questions on initial conditions or boundary values? Okay. Just to note here with the solving simultaneously, here it was a second order differential equation. So it was 2 equations, 2 unknowns. Pretty easy to solve. If you were given a third order differential equation, then that would be 3 equations, 3 unknowns. Okay, makes it a bit more difficult to solve, but you've done your MATH162, you know how to solve that. Okay. So it will always be n values given, n unknowns, so your n by n matrix. Yeah, and then just some terminology. Okay, a differential equation with a set of initial conditions. Right, so 1 initial condition if it's first order, 2 initial conditions if it is second order, 3 initial conditions if it's third order, and so on. So just a set of initial conditions is called an initial value problem. Okay, IVP. So you'll see that abbreviation a lot in the textbook. Okay, so imagine it's test time. The question will state, solve the initial value problem. You'll be given a differential equation, whatever it might be. You'll be given a set of initial conditions, and then you need to go through the process. So if it is second order, you'll get your 2 linearly independent solutions. So that's step 1. Show they're linearly independent. Then you don't have any more to find. Then you get your general solution, A times the first one plus B times the second, step 2. And then step 3, you use your initial conditions to then find A and B, or A, B, and C, or however many you get. Okay, so altogether that is called an initial value problem. Then a differential equation with the set of boundary conditions is then called a boundary value problem. Differential equation. So a differential equation with a set of boundary conditions is called a boundary value problem. Okay, and you'll see this as BVP. Okay, so again, the question will be some differential equation, some sets of boundary values, and we'll say solve this BVP. And then you go ahead and follow the steps for that. Okay, any questions on these two? No. Okay, so we've got some homework problems, then we'll have a little break and then continue with the next parts. Okay, determine the general solution and particular solution for the following. Okay, number 1, y prime is equal to 6x minus 3, with y at 0 is 4. Okay. Number 2, y prime is equal to 2x plus 1, with y at 0 is 0. Number 3, y double prime, so second order, is equal to 4x. And since it's second order, we need 2 initial conditions or 2 boundary values. Here it will be y of 0 is 5, y prime of 0 is 1. So what type of condition is that? Initial, yes. Okay, and then number 4, y double prime is equal to minus x plus 1, with y of 0 is 0 and y of 1 is 2. What type of problem is that? Boundary value problem. Good. Okay, so take that down. That will be the homework for this chapter. So we're going to have a, let's say, 10-minute break. Okay, and then we'll continue with the next section.